Hello and welcome. In this video, I'm going to give you a whirlwind introduction to some key concepts in probability. And I'm doing this because probability is the mathematical foundation on which statistics and statistical inference are built. So let's start by talking about random processes. A random process is a situation where we know some outcomes that could happen, but we don't know what particular outcome will occur if we do something. So if we flip a coin, we know that that coin can land on heads or on tails, but we don't know which is going to land on ahead of time. So coin tosses, rolling a die, drawing a card from a deck, hitting shuffle on your iPod, and all sorts of other processes are random. We know a set of options that could happen, but we're not entirely sure which one is going to happen. Probability is something that we can discuss in terms of a random process resulting in an outcome and which of the outcomes is most likely in a random process. Statisticians argue with one another about what the definition of probability should be. Instead of getting off in the weeds of this particular statistical debate, we're just going to adopt what's called the frequentist definition of probability, which says that the probability of an outcome is the proportion of times that outcome would occur if we observed a random process an infinite number of times. So if we observed an infinite number of flips of a fair coin, the probability of heads is the proportion of heads that we would get if we observed that infinite process. Probability can range between 0 and 1. So, in this notation, if P of A, the probability of A, is the probability of that particular outcome, A, that probability can be equal to 0, it can be equal to 1, it can be anywhere in between, but it can't be less than 0 or greater than 1. We have a lot of intuitive ideas about probability, so let's talk about an example of something like that. Which of the following events would you be most surprised by? Getting exactly 3 heads if you flipped a coin 10 times, getting exactly 3 heads if you flipped a coin 100 times, or getting exactly 3 heads if you flipped a coin 1,000 times. Of course, the most surprising of these outcomes would be getting 3 heads and 1,000 coin flips. Because we know that a fair coin has a 50-50 probability of landing on either heads or tails, we would expect that we would get roughly 500 heads in 1,000 coin flips, so getting only 3 would be a radical departure from what we expect. This is an illustration of something called the law of large numbers, which says that the more observations that we observe, the proportion of occurrences with a particular outcome, so say the proportion of coin flips with a particular outcome heads, that proportion will converge to the probability of the outcome P. So if theoretically the probability of getting a head is 0.5 in a coin flip, we would expect that the proportion of occurrences that are heads, as we collect more and more observations, that proportion is going to get closer and closer to 0.5. Let's talk about a couple of different kinds of outcomes that we might be interested in. Disjoint outcomes are mutually exclusive. These are outcomes that can't happen at the same time. So, for example, if I flip a coin, that coin cannot simultaneously land on heads and land on tails. If I draw a card from a deck, that card cannot simultaneously be an ace and be a queen. If you take a given class, you cannot simultaneously pass that class and fail that class. Some outcomes, though, are not disjoint. They're not mutually exclusive. So, for example, I could draw a card from a deck, and that card could be both an ace and be a heart. Or a given student could be taking multiple classes in a semester and get an A in statistics and get an A in economics. Those things are not mutually exclusive. A probability distribution is a representation of all possible events that could happen in your trial, as well as the probabilities with which those events occur. So if I wanted to make a probability distribution for flips of a fair coin, all the possible events are heads and tails, and the probability of each of those events is 0.5. In a probability distribution, all of the events that I list out must be disjoint. They must be mutually exclusive. And every probability, of course, must be between 0 and 1, otherwise it's not a sensible probability. And finally, all of the probabilities must add up to 1. So the probability distribution has to contain everything that could happen. So I couldn't have a probability distribution that just had heads in my fair coin flip example, because the probability of heads is only 0.5, and I would need to add in the other outcomes to make my probabilities total to 1. So let's look at another example, just a quick one. The probability distribution for the results of flipping a fair coin 2 times in a row. The possible events are heads and heads, heads and tails, tails then heads, tails and tails. So the probabilities for each of those events are 0.25. In a probability distribution, I have to write down all of the events that could happen. When I do that, I collect the sample space, which is the collection of all possible outcomes of a trial. So, returning once again to our coin flip example, the sample space of an outcome of a single coin flip is heads and tails. Those are all of the options that could happen in that coin flip. If I flip 2 coins, the sample space is heads and heads, heads and tails, tails then heads, tails and tails. Complementary events are mutually exclusive events with probabilities that add up to 1. So heads and tails are complementary outcomes in a coin flip. Those probabilities add up to 1 because one or the other is going to happen, and they are mutually exclusive. They can't happen at the same time. If I draw a card from a deck, spades and hearts are not complementary outcomes because while they are mutually exclusive, they don't add up to 1. However, spades and not spades are complementary outcomes. If I draw a card, it will either be a spade or it won't be a spade. One really key concept in probability and in statistics is the idea of independence. 2 processes are independent if knowing the result of one process doesn't tell you anything about the outcome of the other process. For example, if I flip a coin and it lands on heads, that doesn't affect at all whether the coin will land on heads or tails the second time. The coin doesn't care that it landed on heads once already. The second coin flip is going to be just as random as the first coin flip, and it won't be affected at all by that first heads. If, however, I draw a card from a deck and I set that card aside, I don't put it back in the deck, that does affect the probabilities of drawing cards in future draws from that same deck. So if I draw an ace and I set it aside, my probability of drawing an ace on my second draw has gone down because there are fewer aces in the deck. So drawing cards from a deck sequentially is a dependent process, not an independent process. The relationship between height and weight is another classic example of 2 dependent processes. The taller you are, the more you are likely to weigh, so those 2 variables are dependent on one another. Now, of course, dependence is not the same thing as determinism, so it's not necessarily the case that every person who is tall weighs more than every person who is short. It is possible for someone who's 5 feet tall to weigh more than someone who's 6 feet tall, but it is more probable that the taller person weighs more than the shorter person. So that's the difference between dependence and determinism. Lots of the research questions that we're interested in have to do with disentangling whether processes are dependent or independent. For example, my research question could be about whether having information about somebody's annual income gives me any information about whether they're likely to vote Republican or Democrat. Or I could be wondering if knowing whether a country is a democracy tells me any information about how likely that country is to fight in a war. So I'm asking, are income and voting dependent or independent? Are democracy, regime type, and going to war dependent or independent? Lots of our research questions are built this way. For independent events, this is the product rule that we have for the probabilities of several different outcomes in a row. So if I want to know the probability of getting heads on one coin flip, then getting heads on another coin flip, that's the probability of heads and heads. That's the probability of one multiplied by the probability of the other, because these are independent events. There's a different product rule for dependent events, or a more general product rule that we'll go over a little bit later in this lecture. But here's the product rule for independent events. So for the coin flip example, the probability of getting tails on the first toss is 1/2, and the probability of getting tails on the second toss is 1/2. So the probability of getting 2 tails in a row is 1/2 times 1/2, which is equal to 1/4. Next, we're going to talk about the concept of conditional probability. So conditional probability is the probability that an event A will occur given that a different event B has already occurred. So some of examples of conditional probability questions are, what is the probability that 2 countries will go to war against one another, conditional on both countries being democracies? What is the probability that a person will vote Republican, conditional on that person having voted Democrat in the previous election? What is the probability a patient will recover from her illness, conditional on being treated with a particular drug? So let's look at an example to explore some of these concepts in conditional probability. We're going to be looking at a study where researchers were treating 72 chronic users of cocaine, and those patients were grouped into 3 different groups. One group was treated with desipramine, which is an antidepressant. The next group was treated with lithium, which is a standard treatment for cocaine. And the third group was a control group, a placebo group. And in this table, we can see the results of the study. There are 24 patients in each of those 3 groups, adding up to 72 users total. In the desipramine category, 10 of the people treated with desipramine relapsed, 14 of them did not. 18 people treated with lithium relapsed, 6 did not. And 20 people that got the placebo treatment relapsed, whereas 4 did not. We can ask what the probability of a patient relapsing is. This is what's called a marginal probability. So the probability that a patient relapsed is the total number of patients who relapsed divided by all of the patients in the study. So 48 divided by 72 is about 0.67, about 2/3 of the patients relapsed. The marginal probability of not relapsing would just be the opposite of that. It would be the total of the patients who didn't relapse, 24 of them, divided by all of the patients in the study, 72. So that would be 24 divided by 72 equal to about 1/3. A marginal probability asks about one condition. A joint probability is going to ask about 2 conditions at once. So, whereas the marginal probability asked about the probability of a patient relapsing, this joint probability is going to ask, what's the probability that a patient received the antidepressant and relapsed? So here we're going to look at the patients who are in this category of being treated with desipramine and relapsing. So there are 10 of them highlighted in the table here. We're going to take those 10 patients, divide by the total number of patients in the study to get the proportion of patients who were treated with desipramine and relapsed. There's about 14% of them. And like we talked about earlier, a conditional probability asks about the probability of an outcome A given a condition B. This is calculated as the probability of A conditional on B is equal to the probability of A and B over the probability of B. So you might notice that what this is equal to is the joint probability of A and B over the marginal probability of B. So if A is equal to relapse and B is equal to being treated with desipramine, we calculate the conditional probability of relapsing conditional on having received the desipramine treatment as the proportion of the patients who were treated with desipramine and relapsed over the proportion of patients who were treated with desipramine overall. That's 10 over 72 divided by 24 over 72, which simplifies to 10 over 24, or about 42%. So of the patients who were treated with desipramine, about 42% of them relapsed. We can also reverse this question and ask a different question about the relationship between relapse and this particular treatment. While before we were asking what the probability of relapse was conditional on receiving desipramine, now we're going to switch that up and we're going to say, what's the probability a patient received desipramine conditional on knowing that the patient has already relapsed? So out of all of the patients who have relapsed, how likely is it that a particular patient in the relapse group received desipramine as their treatment? So the probability of receiving desipramine conditional on relapsing is 10 divided by 72, so the 10 patients who received desipramine and relapsed over all 72 participants, divided by 48 over 72, all of the patients who relapsed divided by all of the patients in the study. This simplifies to 10 over 48, or about 21%. We can also do the same exercise for the other treatments. The probability of receiving lithium conditional on knowing that the patient has relapsed is all of the patients who got lithium and relapsed over all of the patients, 18 over 72, divided by all of the patients who relapsed, divided by all the patients in the study. That simplifies to 18 over 48, or about 38%. And then in the placebo category, there were 20 patients who received the placebo and relapsed, and there were 48 patients who relapsed overall. So that's going to simplify out to 20 over 48, or about 42%. So earlier in this lecture, we talked about a product rule for independent events. So we found that the probability of getting 2 heads in a row in fair coin flips was the probability of 1 head, which is 0.5, multiplied by the probability of the second head, 0.5, which gave us the 0.25 probability of getting 2 heads in a row. This rule for products is different if the events are not believed to be independent. So the joint probability generally, if A and B represent 2 outcomes or events, then the probability of A and B is the probability of A conditional on B times the probability of B. So this is just a rearrangement of the conditional probability formula that we already looked at. And I have this down here where you can see and compare these two formulas. The conditional probability formula says the probability of A conditional on B is the probability of A and B divided by the probability of B. If we multiply both sides of this equation by B, we get that the probability of A and B is the probability of A conditional on B times the probability of B. So we want to know the probability of 2 things happening, of A happening and B happening. So we find the probability of B happening and then multiply that by the probability of A happening given that B has already happened. This gives us the probability of both of those things happening at the same time and takes into account the conditional relationship between A and B. If the probability of A conditional on B is just equal to the probability of A, this means that the events A and B are independent. That just means that the probability of A doesn't change based on what the outcome of B is. So knowing B doesn't give us any information about the likely value of A. If we go back to this conditional probability formula that we looked at before, we know that if A and B are independent, based on the product rule for independent events, that the probability of A and B is the probability of A times the probability of B for independent events. So we can substitute that into the conditional probability formula. We find that the probability of A conditional on B is equal to the probability of A and B happening over the probability of B, which is then equal to, because we do this substitution, the probability of A times the probability of B over the probability of B, which is just simplified down to the probability of A. I know that's a little complicated, but try to understand the conceptual intuition behind that. If B doesn't affect A at all, then the probability of A conditional on B is just the probability of A. If I drink 2 cups of coffee in the morning, rain or shine, then the probability of me drinking a cup of coffee in the morning, conditional on it raining, is just the probability of me drinking a cup of coffee in the morning. I can say what's the probability of coffee conditional on rain, But the reality is that rain doesn't affect my decision of whether to drink coffee at all. So my probability of having coffee is just my probability of having coffee. So that's just been a really rough introduction to some key concepts in probability, and especially to the concept of independence and dependence and conditionality, which is going to play into all sorts of things that we talk about through the rest of the semester. So I would really encourage you to read up on the sections of probability that are assigned in your textbook reading for this week. And I will see you in the other videos for this week where we're talking about probability distributions.